So this is our lecture 4 of this topic, dual nature of radiation and matter. So till now, first we have discussed the cathode ray, and after that, in first class we have discussed the cathode ray and the experiments of some photoelectric effect, determination of Q by M ratio, that stuff. And later we have discussed totally in detail. We have discussed the photoelectric effect, the experiment, the observation, the explanation, and at the end we have introduced some property, particle particle property of wave of light, so that we can able to explain the observation of photoelectric effect. So, and we have seen that using the concept of photon is a particle of light, we can explain the all observation of the photoelectric effect, which was not possible by considering light as a wave. Okay, so to explain that, we had to consider particle nature of the light. Okay, so in this discussion, in this class, we will discuss the wave nature of the matter, the totally complementary one. So today our discussion is, I think, is visible, wave nature of the matter. Basically, we are going to discuss the wave particle duality. Okay, so as we know, we are familiar with two things around us. Actually, we are very much familiar. First thing is matter, and another thing is wave, exactly, wave or radiation. Radiation is also part of wave, so wave in general, wave. So we can see around us there is nothing except these two things, matter or wave. That means this mouse is a matter, this pen is a matter, everything is matter, and this light is a wave, as we know before. Sound, I'm talking, the sound is a wave, and lots of radiation are there. We have discussed the all frequency. Light has a all type of radiation: cosmic ray, gamma ray. After that, micro. I'm not going to the chronology wise. Just all other wavelength. There are lots of radiation. So around us, everything is either matter or wave, except that there is nothing, right? Okay. But how we characterize these two things? One important thing is mass, right? For matter is always associated with some mass. This pen has some mass. Certainly, this pen has some mass. This mass is defining this pen as a matter, actually. Okay. So mass is the most important criteria of the matter. Wave generally does not, not generally, does not have any mass, or more precisely rest mass. What we consider mass, that is actually the rest mass. Okay, I'm not going into the concept of rest mass or other things, but as we know, what we understand in context of mass, that is the rest mass. Actually, the mass when the particle is in rest, that is the rest mass, and that mass is, there is no rest mass for the wave. We consider the light or sound. We know that there is no as such mass of the light or sound. So for matter there is a mass. Now for wave, let's say it's considering the light, because till now we are discussing everything in context of the light, the photoelectric effect or everything. So observe that what we observe that light also has some particle characteristics. Particle means the matter. Matter has a particle and particle has a mass, actually. So particle nature also light has. And that particle is called photon, right? We discussed in last class the light is a quantized particle. We are not considering light is a continuous wave like that. We can consider it like these are the particle of the light, actually. Also light has wave property, that's why we can visualize things like this, but this is not the actual picture. This is just an artistic demonstration. Actually, there is no, anybody does not know the actual picture of light, how it actually looks like, whether it's wave or matter. That is not known. We are aware of that light has both nature, that is particle nature and the wave nature. How? Because light shows the refracts, the refraction. I'm not writing. Okay, it's known. I'm telling in verbally. Light has reflection, polarization. These properties. These property establish the light is a wave, and considering light as a wave, electromagnetic radiation, Maxwell also proves not proves. Maxwell also derived the speed of the light in vacuum, which matches exactly with the experiment. Not exactly, okay, 99.99% we can say that. Okay, with the experimental observation, which is 3 into 10 meter per second. So we suggest that light essentially is a wave. But after that, in photoelectric effect, what we observe that considering the wave nature of the light, we are not we can't make explain the photoelectric effect, the observation of the photoelectric effect. Explain those observations, we had to consider the particle nature or the quantized nature of the light, and the quanta of the light is called photon. That's it, which has the energy. That energy is proportional to the frequency of the light. That means E is equal to nh nu actually. The energy of the smallest quanta has the energy is h nu. That is the minimum energy of the quanta has h nu. That is a photon, and that is as the other quanta of the not quanta, other wave packets actually, or wave packets of the light has the energy in the multiple of that quanta. That means nhν. We had already discussed this. So this wave packet, this is signifies the particle nature of the light. These particles are called photon. Okay, good. So now, if wave can be represented as particle, not represented, wave can have the particle nature, then also particle or matter can also have some wave nature. It may be na, vice versa. It has already shown for light. This is possible or not. We have to look for that. Okay, so let me first do it for wave or light. Okay, for light, this is not known. Okay, this we already know from the photoelectric. For light, what we obtain that E is equal to h nu. Okay, when what is the h? H is the Planck constant, which is 6.62, sorry, 626 into 10 to the power minus 34 joule second. Nu is frequency, which is c by lambda, where c is the speed of light in vacuum. Okay. Also, we know that for light is equal to mc square. Okay. Okay. Not for light actually. For when this is when some particle, when some particle is converted to the energy, then this amount of energy will be released. If the particle has the mass m, then the energy of that particle is mc square. Let's say this is a particle of less mass m. If this particle is totally converted in form of energy, then the energy will be mc square. M is the mass and c is the speed of the light. We already know this. This is the Einstein relations. Now we are considering this photon. Let's say this is the photon. Photon means the particle of the light. This has also some mass. This is not the actual the rest mass. This is because light don't have any rest mass. Okay, I'm not getting in that concept, the rest mass concept, but let us consider this light has some mass m. Light has mass actually. So then also that photon has energy mc square. Again, from photoelectric effect, we have seen that energy should be h nu. Now, if we equate those energy, what we obtain is trivial. H nu is equal to mc square. We can write these things. And now what we can write, nu is equal to c by lambda. Then we can write that mc, this is actually h by p. This is the general equation. Lambda is equal to h by p for the light. Why I'm writing p? Because p is the momentum. This is the momentum. this m is not the rest mass, what I am saying about that for light. So that's why it's better to write in terms of momentum p, that is a general representation. That's why I'm writing the momentum. If we can write also the mc, but we have to mention that m is not the rest mass. Okay, so lambda is equal to h by p. This relation we can prove for the light, and we have proof for the light. This supports the wave nature, and this supports the particle nature. So this equation is the de Broglie or the Bro equation, what we can say. This equation actually connects two properties, the particle nature and the wave nature of the light. Okay. So what de Broglie or the Broglie, I'm saying that the Broglie said that if wave if wave can have the particle nature, then also in the similar context we can also say that the particle or the matter also can have some wave nature. Okay, and for them also this equation will hold. This equation lambda is equal to h by p. This equation will hold for matter as well. Like we can say electron, proton, every matter, not only electron, proton, this everything, ball, pen, everything. For everything, this, that's why this is a general equation, no? That's why I write this equation h by p. Is a momentum. It can be for light, it can be for some classical macroscopic element as well. But if we write in terms of mc, then we have to write for macroscopic element. For matter, we have to write mv, where m is the rest mass, v is the velocity. For light, we have to write mc, where c is the speed of light, and m is not the rest mass. So that's why it's better to write the p for making the equation general. Okay, so this is our lambda is equal to h by p. P is the momentum. Okay, so this is de Broglie equation, which is let me write. So this is the de Broglie equation, which actually signifies the dual nature of matter and wave. That's it. Okay. Okay. Now one question may appear that if this equation correct, then why we can't see this, let's say this. We can't see this as a wave, no? This is the particle. Or not matter. Matter has particles. So when I'm saying the particle, that signifies the matter. So this has a particle nature. That means this is the matter. But we can see that, no? This has a mass, this is matter. But de Broglie equation says that this also has some wave nature. Can we see that? We are not able to see, right? Why? Whether this equation correct or not, we have to prove. We have not proved. We can't prove the equation because we have written the equation with the same analogy the wave has, light has. So we are not going to prove the equation because we can't prove the equation. Actually, we are giving some physical explanation. Okay. So in that case, we are not getting any wave nature of that particle of the matter. Why? Why? Because let us do some mathematics, right? Let me write. Okay. So take a macroscopic classical particle which has a large m, and let's say it is moving. If it is in rest, then we are not considering. Let's say it has some velocity. If I throw it, it has some velocity v. It has some constant velocity v. So its mass is m, its velocity is v. Okay. So we are considering this is just 0.12 kilogram. We are considering the exact value in the NPTEL book has. We can take any value and we can make the calculation, guys. As such, no violation of these things. Okay, let's just speed. Speed is, they have considered 40 meter, 20 meter per second. Okay. So if we put these values, what will be the momentum? P, momentum P equals to mv. That means 0.12 into 20. What will be the unit? Kg meter second inverse. Okay. So what will be the value? 1.2, 2.4. So this is the momentum. So now if we calculate the wavelength associated with this matter lambda, this wavelength is called de Broglie wavelength. Okay, this equation is the de Broglie equation, and let me write it. This is called de Broglie or the Broglie wavelength. Okay, so the wavelength is h by p, that means 6.626 into 10 to the power minus 34 joule second divided by the momentum, which is 2.4 kg meter second inverse. Okay. Now, what is the definition of the joule? We have to know that, then only we can calculate the value. The value, this is very trivial. This is 2.76 into 10 to the minus 34. What will be the unit? That we have to know. Okay. Where? Okay. Joule. This is joule. This is the unit of the energy. This is the unit of the energy. We can energy is associated with work done. That means force into displacement. What is the unit of the displacement? In SI, it is meter. What is the force? Force is the mass into acceleration. So what is the unit of the mass? Kg. What is the unit of the acceleration? Acceleration is velocity, time. What is the velocity is meter second inverse, and again time, so it's meter per second square. So total, what will be the unit of the joule is kg meter square second is, say, time to the power minus 2. If we put it instead of joule, so joule second will be kg meter square, and it will be second inverse, because here s to the second to the power minus 2, power was the minus 2, and again there was a 1 second, so it will be minus 1. So this will cancel out, this will cancel out, only one m will be there. So this is the meter, and wavelength should have the unit in meter or in the length unit. So what we can see, 10 to the power minus 34 meter. If there is some way having the wavelength in that 10 to the power minus 34 order, we never ever can't visualize, not visualize, can feel even. So if the particle having the mass 0.12 kg, considering this type of particle, if it has some velocity, then obviously, though it has some wavelength, de Broglie wavelength associated with this, according to the de Broglie equation, but that wavelength is very, very, very short wavelength. We can't even feel that wavelength. So this has some wave nature, but this wave nature is not precise. It's not what we can say, that we can't actually feel that wave nature due to that the wavelength of the de Broglie wavelength is very, very small. It tends to 0 actually. Okay. So now, but then how we can prove the hypothesis, the equation, de Broglie equation? Because de Broglie gave that equation hypothetically, because for light it is established. Light, we can establish that lambda is equal to h by p, but for matter it was just ad hocly said by the de Broglie, So we have to justify this equation, right? So let me try to give some justification. Okay. So this wavelength is beyond the measurement, so we can't measure this kind of wavelength. So we can't make any comment. But what we can do, let us take some, we can take the macroscopic particle, we have to consider the electron. Okay, because if we see, this is inversely proportional with the mass, because momentum is there. So if the mass is heavier, then essentially the wavelength will be very small. That's why. So we have to consider the electron. Okay, let's say electron, and there is some potential. Okay, V potential is applied. Let's say it's plus its minus. There is some, okay, like this. And we put an electron here. This is an electron which is in rest. This is totally in rest. This is not photoelectric effect. We have there is a electron is totally in rest, and then we apply some potential difference, potential bias. The potential is V. This is capital V. So there will be some force, not this way, in this way. There will be some force. What will be the force? That is the field V, and it has a charge. So it will be EV. E is the charge of the electron. We are considering the electron. So electron has the charge E, and its potential is V. So EV. So this is the potential energy given by that field to that electron, and this potential energy will be converted to the kinetic energy K of that electron. So potential energy, we are giving the potential, which essentially increases potential energy, and it converted in kinetic energy. What we can think that this is that potential difference. V is the electron is there. We put the electron in rest form in between that, and we are applying the potential difference. What will happen? This electron will accelerate, okay, according to the field. So kinetic energy, some kinetic energy will be because essentially in first case, when we are giving the electron, just we are not applying the potential difference, it is in rest form, there is no kinetic energy. Okay, when we are applying the potential difference, that potential difference essentially give the kinetic energy to that electron, and that's why it moves. Okay, potential energy converted to the kinetic energy. Considering that this is some ball, if we make this, okay, what happens is here it has potential energy, no kinetic energy. If we leave it, then the potential energy is converted to the kinetic energy. Same thing. Here also some potential difference is there, no? Okay, so we can write this EV is equal to K. K is the kinetic energy. And what is the form of kinetic energy? We know that half m v square. V square is the velocity of that electron. Okay, so we can write this. So what we can, and what is the definition of momentum? Momentum is mv. Okay, so we can write this p square by 2m. Okay, p square is m square v square, and if we divide it to m, we essentially get the kinetic energy. So what will be the definition of P? P will be root over 2 MEV. If P is this, then the de Broglie wavelength associated with that electron will be H by P, will be H by root over 2 MEV. Again, we can see that H is known to us. M of this is the mass of the electron. This we also know. This is the charge of the electron. This is also known to us. This V, this is the voltage difference, and that is in our hand. So we can control that voltage difference. So essentially, we can calculate the lambda. So if we put the value of everything, then we obtain that it is 1.227 divided by V nanometer. Nanometer means 10 to the power minus 9 meter. Okay. So now let's say V is 120 volt. If V is 120 volt, then the lambda will be, we can put this value and we can calculate, it is 0.112 nanometer. So this is some wavelength which we can make some experiment on this wavelength, whether this is correct or not. Because in crystal, there is some plane in crystal, the Miller plane, something Miller indices there. In between the solid crystal, there is some in between plane, and between there are plane, and the distance between the plane is in the order of the nanometer scale actually. So we can make some experiment, okay, with X-ray diffraction. If we make XRD, X-ray diffraction, okay, so if we do that experiment, we can show that exactly the wavelength is this. You can check whether this value is correct or not with that XIT fraction experiment, and it is established that the value is correct. And that means the hypothesis that was considered by de Broglie is correct. The matter wave, the dual nature of the matter and the wave, that was correct. And as a consequences, he was awarded Nobel Prize in Physics in 1929, discovery that wave nature of the matter, or essentially the electron. Okay, so this confirms that yes, as light has the wave nature as well as the particle nature, the particle or the matter can also have the wave and particle both natures. So light, matter and wave, though this seems very different from each other, actually they are not the different things. Matter is also has some wave nature, it has also some the wave has also some particle or the matter characteristic. That means everything is same. Everything has both nature, matter, particle nature and wave nature. For something, some elements, wave nature is dominating. That's why we essentially consider that things as wave. And for other elements, particle nature is dominating over the wave nature. That's why you're considering those things as the wave, as the matter. Okay, so this is the just difference. But both matter and wave both has the same, both has wave property and matter property as well. Okay, so now we will discuss that. Okay, this Heisenberg uncertainty actually is the backbone of the quantum mechanics, right? Okay, very important. This is the backbone of the quantum mechanics. Okay, we are not getting into the quantum mechanics in details, but what is the Heisenberg uncertainty principle? This is a classical particle. First, we have to understand what is the classical particle and what is the quantum particle. Okay, classical particle are those particles which we can see around us. Everything is the classical particle. Everything. These are actually macroscopic particles. Okay, macroscopic particle. That means these are actually the matter. Matter part is very much dominating. Wave nature is very less. We don't even consider those as a wave. Okay, these are called the classical particle. Everything around us we can see. These all are the classical particle. This classical particle has a feature. The energy of this particle is continuous. Means any energy it can have. This is the classical particle. We can give any amount of energy. There is no restriction. There is no restriction. It can have the energy 1.2 joule kinetic energy. Let's say if we throw it, then it will have some kinetic energy. It may be 1.2 joule. It may be 1.1119 joule. If each energy it can be to it can be provided. Okay. There may be some experimental foundation, but that is not due to that particle. That is not due to this matter. That is not features of this matter. This is our limitation. We can't give let's say 1.111119 joule. Okay, precisely we can't give that energy, but that is our fault. That is not features of this particle. But what is the quantum mechanical particle is that quantum mechanical, if we classify quantum mechanical particle, these are basically microscopic particles. Okay, due to microscopic nature, it has both matter and wave nature. Wave nature is very much prominent. Let's say for electron, for proton, this type of particle. This particle has eminent wave nature. So these are matter and as well as wave. What happens due to this property? Energy is quantized. Okay, electron can't have any value of energy. We'll study that in future. We'll study that for electron, the energy is totally quantized. In light case, we see now that the particle of the light can't have any value of energy. It will be the integral multiple of that h nu. H nu is the minimum energy of that quanta, light quanta, h nu. So the energy of the particle, light particle, photon, can have the energy in the integral multiple of that H2. That is the NH. It can't have any value. It can't be 1.5 H or 2.5 H. This is called the quantization. The quantum mechanical particle also has, that's why it's called quantum mechanical particle, because for those particle the energy is quantized. There is some restriction. Any energy can't have. Okay. For electron, we'll see that when it in hydrogen atom, we'll study in 11 in probably we have studied that in atomic structure. In atomic structure, we have studied that for the electron, it can't have any energy. It has a restriction that M here should be equals to NH cross. That should be satisfied. Then only electron can stay there in that orbit. That's why uh, things are called orbit. The energy is preserved and those cases, right? Electron can't have any energy. Okay, that's why that is quantized. Energy is quantized due to these features. These particles are called quantum mechanical particle. For this type of particle, entire physics is different. Entire things are different. One of the major difference is that uncertainty. Because for classical particle, there is no uncertainty. We can measure this momentum and the position of the particle simultaneously. There is no as such as uncertainty. But for quantum mechanical particle, as that has a wave nature simultaneously, there is some uncertainty. Okay. Uncertainty means you have to first understand this. These are the very, very important things. Let's say it is some particle. It may be classical, it may be quantum. Let's say it's classical. First, classical particle is. So it has some position that is defined by x coordinate. It has some momentum that is defined by p. Okay. So del x is the uncertainty in the position, which is we can write how we can write things like this, right? Something like that. I'm not okay. I'm not getting into that. Del x is the uncertainty. Uncertainty means it essentially signifies the x minus average of x. Okay. How we can understand that? Let's say if there is a player, any batsman, we consider that it has the average value, average run is 50. That means we think like that in every match he makes 50 runs. Now in one match he can make 60, one match he can make 100, in one match he can make 0 as well. So what is the deviation? We have studied things, are not standard deviation thing, variation, standard deviation in mathematics. It's the same thing. Deviation is 40, 10, 0, 50. These are the deviation. Okay, this is deviation is essentially signify this uncertainty. That is the del x. Similarly, in case of momentum, that is also the uncertainty in momentum. That is the del p. But Heisenberg uncertainty says that for quantum mechanical particle, this would be h cross by 2. Okay. For classic h cross is, what is the h cross? H cross is h by 2 pi. Okay. These uncertainties would be there. Every quantum mechanical particle has uncertainty in the position and the momentum. Not only, there are all other forms as well. Del E, del T, there is some uncertainty in similar kind of uncertainty as well. In angular momentum case also, but we are not getting into that. We are considering that position and momentum. In case of position and momentum, there is some uncertainty. This is uncertainty. If del x del p is 0, that means there is no uncertainty, right? In classical particle, there is no uncertainty. We can measure both. Both the velocity and both the velocity means essentially the momentum, because we can write these things like del x del v to m. similar things because M there is no uncertainty in here for electron. M is M. So this is our uncertainty relation. Now this holds for the quantum mechanical particle only. Okay, for classical particle we can make del P 0, then also we can have del X 0. Okay, for classical particle, this is okay. Let me write. This is the uncertainty, Heisenberg uncertainty. This was given by the Heisenberg. Heisenberg uncertainty for quantum mechanical particles. For classical particles, if del X 0, that means there is no uncertainty, then also del P can be 0. What happens? Okay, then also del P can be 0. That means in momentum also there is no uncertainty. What does it mean? That we can measure both momentum and the position of the particle simultaneously. Okay, both. Now, this is for the classical particle, but for quantum mechanical particle, there is, because for classical particle there is no uncertainty relation. This equation does not hold for the classical particle. This is for the only quantum mechanical particle. Okay, so for quantum mechanical particle, if del X is 0, then what happens? Del P is infinite. Okay, if we put del X 0, del P will be infinite. And if del P is in 0, then del X will be infinite. This is the meaning of the uncertainty field principle for quantum mechanical particle. So if we del X 0, that means if we try to measure the position of the electron precisely without any uncertainty, then we can't measure the momentum of the particle. That will be infinitely uncertain. It can have value 0 to infinite. And similarly, if we try to measure the momentum of the particle without any uncertainty, that means precisely, what happens? The position will be totally uncertain. Del X can be infinite. Okay, what does it mean? To explain this, we have to consider the wave nature. We have to consider the wave nature of particle. Okay, so let's say we are considering electron. Okay, now if for that electron, if del X is 0, what will happen? The del P will be totally infinite because there is infinite uncertainty. Okay, and similarly, if del P is 0, then similarly, as I written, del X will be infinite. The bond probability interpretation means that the electron is not localized. If del X is infinite, that means that is not localized. It can have any value. Okay, in general, matter wave, in general, electron, this is a matter wave. It has matter particle nature and wave nature as well. Okay, wave nature means there is some wavelength. If it has some wave nature, in Ribogli equation, wave nature is represented by the lambda wave, and the particle nature is represented by the momentum mass. These are the two things. Huh? Okay, so wave nature, that means there is some lambda. Now we know the wave packet concept, right? These are the electron, right? So it has some wave nature. For light also we see something like this. This is the wave nature, wave particle duality things. It has as a wave nature as well as the particle nature. Okay, so what? Yes, right. So if there is some uncertainty, let's say now we are going to prove the uncertainty relation using the de Broglie hypothesis. That is our task actually. Okay. Now let's say if del P is 0, we are trying to measure the momentum precisely without any uncertainty. So if del P is 0, it means that del X is infinite. Okay. Del X is infinite. What does it mean? It means that this is the matter wave and this will goes on. Okay. What is the lambda? It's very important to understand. This distance is the wavelength, lambda. Okay. So as we are precising the lambda, then the X that is not bounded, it is infinite. That means the uncertainty in the position is infinite. Lambda is precise. If lambda is precise, from Heisenberg, from de Broglie equation, lambda is equal to h by t. If there del lambda, we can write del. Similarly, in del p, that means if there is some uncertainty in lambda, then there is some uncertainty in momentum according to that de Broglie hypothesis, de Broglie equation, not hypothesis. So lambda is totally precise here. It means that the momentum also precise. Momentum is precise means del p is 0. So if del p is 0, we can see that the del x is infinite, right? From this figure. This is the features. So it proves the Heisenberg uncertainty. Now in the reverse case, let's say del x is finite. Essentially what happens? If del x is finite, then del p is also finite. Then only del x into del p, this thing, right? So if del p is not if it is not finite, it is 0. In this case, then del x will be infinite. But in general, del x is finite, and if del x is finite, then what will be the form? What will be the form? Something like this. Okay, it has to vanish here. Then only we can say that the del x is finite. This is the del x. If it is a particle, then this is the position of that particle. This is the coordinate. This is the position of the particle. There is no uncertainty. 0. Del x is 0. This is for classical particle. But we are not considering the classical particle because we know that for classical particle there is no uncertainty relation. It can have 0 uncertainty in both position and momentum simultaneously. We are considering the matter wave. This is the matter wave. This is the matter wave. That's why it is a particle. This is a particle, but it has some wave nature. That's why we have written like this, drawn like this. But it has uncertainty in position. That is this. This is the uncertainty in position del x. So if there is some uncertainty in position, there will be some uncertainty in momentum as well. How we can say that? Now, if we break down this graph, this is not a single wave. We can say that this is actually lots of waves. Some has some other phase factor like this, and lots of wave having different lambda. If we merge those waves, then we can have as a net wave packet. This is called some wave packet features. Group wave, we can think like that. Lots of waves are there. If we make them together, then the net wave will be like this. And this has delay. But if we break down, then it has many waves, right? Many waves means there are many lambdas. So lambda is not precise. There is so many lambdas. Lambda is not precise. So if lambda is not precise, that means momentum is not precise. So if momentum is not precise, then del p is greater than 0. So if del x is greater than 0, it signifies that del x is greater than 0, then del p will be also greater than 0. We can explain like this. If the del p is 0, that means the lambda is precise. If we make the lambda precise, what will happen? Del x will be infinite. Okay. That means de Broglie hypothesis essentially complement the Heisenberg uncertainty principle. Okay. So here also these two figures are given. I think it's visible. Okay, this part. Okay. Okay. So there are lots of wavelength and there is some central wavelength. Again, here is some, this is central X. Then there will be deviation. In that construct, first we have defined uncertainty. What is the uncertainty? Del X means X minus mean of del X, mean of X. The standard deviation. Standard deviation means there should be some mean value, and around that mean value there is fluctuation, something like that. That is uncertainty. Uncertainty in lambda means there is some mean value of lambda, central value of lambda, and around that central value the lambda is varying, and there are lots of waves, so there are lots of lambda. That means uncertainty in lambda is there. So as a consequences, there is some uncertainty in momentum as well. So del P will be zero, or greater than zero. If del X is greater than zero, del P will be also greater than zero. Okay. So I don't think anything left here. No. Next day we'll study the Davisson-Germer experiment and the matter and the probability interpretation of the matter wave. That's it. These things we have defined, right? The Planck's constant, that is the H, stopping potential, work function, threshold frequency, de Broglie wavelength, everything is defined. So just we have to, in next class we'll finish that Davisson-Germer experiment and our syllabus will finish. After that we'll do the exercise, some exercise from this overall chapter. That will take one class, and last class we'll make some summary and the equations, some charts, this type of thing. Okay, so in tomorrow's class we'll discuss these things. So let me stop today. So in this class we have discussed the de Broglie hypothesis. That means the as we know that from photoelectric effect, as we know that particle dual, light has some wave nature as well as some particle nature. From that, hypothetically, de Broglie said the de Broglie equation, which essentially signifies the wave particle duality, and experimentally we have also studied that from experimentally it can also be verified for electron giving some potential, and for that electron we can measure the de Broglie wavelength, and we can check in experiment, and that experimental checking satisfied that the de Broglie hypothesis is correct. So de Broglie equation is valid for both every particle and wave. And after that we studied the uncertainty relation and how the uncertainty relation and de Broglie equation complement each other. We also studied that, and that uncertainty relation is totally valid for the quantum mechanical particle. For classical particle, there is no uncertainty. We have defined the classical particle, what is the classical particle and what is the quantum mechanical particle, how we can differentiate those, and the entire physics is different for the quantum mechanical particle. We studied that. For classical particle, everything is precise. We can have both things precise, but quantum mechanical particle, there is some uncertainty in position and momentum. And for quantum mechanical particles that are essentially have some wave nature, that's why it is called the matter wave as such electron. But for classical particle, though the de Broglie hypothesis is valid for those particles as well, but the wave nature is very dilute. That means the wavelength is very less, so we don't even consider those wave nature. That's why that particle are called classical particle, and energy of that particle is continuous. Or quantum mechanical particle, the wave nature is also important. That's why it's called matter wave, and both properties are important. And as a consequences, it has discrete energy level. It can't have any value of energy. It has quantized energy levels, so it's called quantum mechanical particle. And entire physics is different for this type of particle. Most importantly, these particles have wave nature, and these particles follows the Heisenberg uncertainty relation, which means that we can't even measure both position and the momentum of the particle precisely and simultaneously. So and that Heisenberg uncertainty is well also satisfied by the de Broglie hypothesis. Okay, this was our summary of this class. Okay, so let me stop today. Tomorrow we will discuss the next part, the last part of the topic, Davisson-Germer experiment, and our topic will be completed. Thank you.